Hello there. So, we are continuing our discussion on the equations of motion for generalized single degree of freedom systems, and we are continuing with equations of motion. And today what I am going to be doing is I am going to be looking at the possibility of developing the same equations of equilibrium, but last time I looked at trying to take, I drew this particular problem, right. I took this particular example problem and tried to solve it by writing the moment as the equation of equilibrium. Now, in general, it is all very fine for us to say that look, this is a it's a determinate system. So, we can find out we can actually write down equation of equilibrium, okay. But it is always a good idea to use some alternate approach to the equation of equilibrium, and the most common approach that we know today is the principle of using the principle of virtual work, okay, to replace the equation of equilibrium, and the specific method that of the virtual work principle that replaces equations of equilibrium is the principle of virtual displacement. Okay. So, what I am going to do is I am going to solve the same problem. Okay. So, the same problem that I solved in the last lecture, okay, excepting that in this one we are going to look at it from the perspective of what? We are going to look at it from the perspective of using the principle of virtual displacement. Okay. So, now let me go ahead and look at it, and let me define theta as my degree of freedom. So, the first and foremost is what? Is the first thing is to look at the what is going to be the displacements at various points, and in fact, at any point x is going to be x theta. Okay. So, that is the displacement pattern that we get, and that is only going to be vertical, right. So, now let us write down the first thing is writing down the forces that this system has. And without belaboring the point, we have done this often enough. By now, we should be able to write this down. What do we have? We have the UDL, which is given by P bar of t. Okay. Then what do we have? We have force here. This is equal to K2 into L by 2 theta. Then we have K1 into L theta. Then we have C into 3 by 4 L theta dot, and we have m bar dx into x theta double dot. So, these are, and this is of course only an infinitesimal, this has to be there is across the board, right. This is everywhere, it is m bar dx into x theta. Okay. So, these are my forces. These are the forces under which the system is in equilibrium. So, how do I use the principle of virtual displacement? Well, these forces, okay, which are in equilibrium. Now, there is actually, these are the forces, okay. And if we look at this, I give this system a virtual displacement, and I will call this virtual displacement delta theta. Okay. So, what is this? L into delta theta, this point L by 2 delta theta, this point 3 by 4 L delta theta, and any point is x into delta theta, okay, any point. So, therefore, what we now do is write down what? The virtual work equation, and virtual work is summation of virtual work is equal to 0. Okay. So, each of these forces undergo these virtual displacements, and we see what are what is the work done. Okay. So, note that this force downwards undergoing upwards displacement does negative work. Okay. So, remembering that, I can now write down all the terms, and that is the virtual work. The virtual work is equal to what? Let us see. Let me take the first one. It is going to be K 1 L theta into L delta theta. So, this is the real force undergoing the virtual displacement, and this is negative because it is negative work. Okay. So, that is the first one. Then the next one is K 2 L by 2 theta. This is the force undergoing the displacement, and this also does undergoes negative work. Then we have C 3 by 4 L theta double dot undergoing 3 by 4 L delta theta, that real force undergoing virtual. Remember that this is the real force, and force into the virtual displacement of that particular point. Then we have the following, which is m bar dx into x double theta double dot. This is the inertial force, this into x delta theta, that is the work done by the infinitesimal length, and so obviously that integrated over the whole length. Okay. And then, so these are the work done by all these, and finally, the work done by that is going to be equal to, that is going to be plus, because note that this undergoes positive work. So, this is going to be plus. Now, let us see, P bar T dx is the load, and that is multiplied by the virtual displacement, and that integrated over the whole length is equal to, that is all the work done. So, that is equal to 0. So, now in this particular case, I am going to just put together all the terms together, okay, and then if you look at it, this becomes the following. Integral 0 to L m bar x squared dx theta double dot, this is minus, then I have minus c into 3 by 4 L squared, the whole squared, into theta dot, minus, and I am going to put inside this K 1 L squared plus K 2 L by 2 the whole squared theta plus 0 to L P bar into x dx and the entire thing into del theta is equal to 0. Note del theta exists on all of them. So, I am just taking the del theta outside is equal to 0. This is the virtual work equation that I have. Now, the virtual displacement is an arbitrary displacement. Since it is an arbitrary displacement, for this to be equal to 0, it implies that the inside has to be equal to 0. If I put the inside equal to 0, what do I get? I get the following. I get m bar L cubed by 3 minus theta double dot minus 9 by 16 C L squared theta dot minus k 1 L squared plus k 2 L squared by 4 theta dot plus p bar L squared by 2 is equal to 0. And if I rewrite this, what I get is that I am going to just put it in this only, this plus this is equal to this. That is all I get. This is my m star, this is my c star, this is my k star, and this is my p star. Note that I have got exactly the same equation that I got by the equation of equilibrium, where I took moments about the left point to be equal to 0, because that's obviously at a hinge it has to be equal to 0. I have used the principle of virtual displacement, where all I have done is I have given a displacement that satisfies all boundary conditions, and I have given a virtual displacement that also satisfies all geometric boundary conditions, and I have just taken the virtual work done and put it equal to 0. Okay. And so, for theta equal to 0, I get exactly the same equation. Now, let us try to see if I use z of t, whether I get exactly the same. So, I am going to redraw the problem. Accepting that now I am taking z of t as my degree of freedom. So, I have this, I have this. I am not even writing down the values, we already know, and this is m bar and I have load. All of this is exactly the same problem that I am solving. So, I am not writing down all of the things, we know this k 2, k 1, c. Okay? We know this, accepting that now I am using z of t as my degree of freedom. So, if I look at the displacement, again this is the same as what we had done last time. Z, if this is z, this is z by 2, this is z by L, and so at any point it is x z by L, this is z by 2, this is 3/4 z. Okay. And having done that, the forces in the various things are going to be the following. It is going to be here, is going to be k 1 z, this is going to be c into 3/4 z dot, this is going to be k 2 into z by 2, and the mass, infinitesimal mass, is going to be m bar dx, that is the mass. It undergoes x by L into theta double dot, and of course, I have my load p star. Okay. These are all my forces that I have. Now, I am going to use the principle of virtual work. So, principle of virtual work, I am going to give a virtual displacement corresponding to the degree of freedom, okay, and find out the work done by all the forces. So, if this is delta z, this is going to be 3/4 delta z. This is going to be delta z by 2. This is going to be equal to x by L delta z. Okay? And so, if I take the work done by all the forces, what do I get? I get it equal to, let me start off, K1 z into delta z. By the way, work done is negative, because if we go back, this is this direction, this is upwards. So, always the work done is negative. Okay? And therefore, what we have is minus, and then we have minus K2 z by 2 into del z by 2 minus C 3/4 z dot into 3/4 del z. Okay. Then what do we have? Then we have minus m bar dx into x by L z double dot, that is the force, multiplied by x by L delta z, that is integrated from 0 to L. That gives me the total work done by the inertial forces, and finally, the work done by p bar of t dx. Okay, that is equal to what? That is to be multiplied by x by L del z. Okay. So that is what we have. This is the work done by the infinitesimal load. So, that has to be integrated from 0 to L, and that is equal to 0. If I rewrite this particular function in another format, what do I get? I get the following. I am going to put them all in the specific part. 1 upon L squared (0 to L) m x squared dx, and this is negative, of course, all of this is negative, dx x squared dx, okay, into z double dot, okay, minus, this is going to be equal to c into 3/4 by 3/4. So, it is going to be 9 by 16 c z dot, okay, minus K1 plus K2 by 4 z plus 0 to L 1 upon L p bar x dx, and this entire thing into del z equal to 0. This is the equation. This is all I have just done is just put together the terms in the previous equation and just put them together. Now, of course, this is an arbitrary virtual displacement. So, obviously, that means this has to be equal to 0, and all I am doing is, if this is equal to 0, I am just putting these on the other side, and so what I get is the following. I get 1 upon L squared m bar L cubed by 3 minus z double dot 9 by 16 c z dot plus K1 by K2 by 4 z is equal to x squared. So, this becomes p bar L upon 2. And so, this one essentially this goes, so it becomes m bar L upon 3. Now, note something very, very interesting, and that is, now if I look at this equation, okay, let me look at this equation very, very carefully. This equation tells me that it is m bar L by 3 into z double dot plus 9 by 16 c z dot plus k 1 plus k 2 by 4 z is equal to p bar L by 2. Okay. So, what is m star? M bar L by 3, C star 9 by 16 C, K star is equal to K 1 plus K 2 by 4 and P star is equal to P bar L over 2. Okay. Let us look at this. This is the beauty of the principle of virtual displacement. The beauty of the principle of virtual displacement is when you use theta as the degree of freedom, the m stars that you get are all given, the m star is a mass moment of inertia, k star is rotational spring constant and p star is a moment. Okay. Now, if z, which is the displacement degree of freedom, if that is my degree of freedom, then what is my m star? My m star, if you look at it, m bar is kg per meter. So, kg per meter by kg, it means this is kg. This is Newton second per meter. This is Newton per meter. This is Newton per meter, this is Newtons. So, if you look at it, the entire equation essentially becomes very, very clean. This is mass, because if it is z, this is mass. So, this has units of mass. If this is displacement, this has units of dashpot constant. If this is displacement, this has units of linear spring constant. And if it is displacement, the P star is a force, and this is the beauty of this. Now, if you look at it, and I do not want to go into it, you will see that if I look at the equations, they look identical if you were to use theta or z, just the fact that z is equal to L theta. If you substitute that in, you will get that equation back. So, the essential point that I want to make is that for a generalized single degree of freedom, your specific equation is consistent. If you use the principle of virtual work, which is principle of virtual displacement in this part, you get consistent. It does not matter where the degree of freedom is defined. It does not matter. As long as the system is a single degree of freedom, the equations of motion that you get are really identical. It is just that they are in some way related to each other. They are really the same equation of motion written in different formats. Okay. So, that is all there is to it. Now, what I would like to do is, once you have this, I can now generalize the equations for m star and k star, etc. Now, this is where the beauty comes, because now if you really look at it, this is nothing but, if you have a displacement as a degree of freedom, then your m star, if you have a linear mass at a particular point, a linear mass, okay, now if we look back at it, let me go back a little bit and define something. If you really look at this, I could define this thing in terms of a xi times z at any point, because that xi times z, if I look at it, I could draw it in this fashion, this z. and I take xi. Xi I take it as 1, half, 3/4, any x. So, this is my xi function. If you look at this, the xi function, then what is my m star in this particular case? The m star becomes, if you look at it, m bar xi squared dx integral from 0. Let us see what this xi function is going to be. Xi in this particular case x squared, you put it x, okay, and so m star then becomes essentially the following, right. If you look at this is m star is going from 0 to m bar xi squared, and you look at xi squared, it basically becomes m bar xi squared. If you look at it, it becomes xi cubed, it becomes m bar L cubed. Okay. I'm sorry, this is not true. Yeah, this is x by L. So, this is x. Okay. So, now m star can be written, if you have m r, it is in this fashion. If you have a linear m, any moment m I is going to be equal to whatever is the xi I squared at that particular time. Okay. If you have mass moments of inertia, you just need to do the slope at that particular point of time squared, and in a sense what happens is you essentially land up having that m star. All you need to do is find out the shape function, find out those values. Okay. Similarly, c star is going to be equal to c I into xi I squared, k star is going to be equal to k I into xi I squared. If I have a theta, if I have a rotational spring, this is going to be equal to xi prime I squared, the slope, and p star is equal to p I into xi I. If there is a specific load multiplied by this, these are all summations, summation, summed up over all the things, this is summation. And then if I have loads, they basically become p star xi I over the length. I mean over the length of which, not 0 to L, let me also say it can be L1 to L2, depending on if you have a particular length over which the load acts. Okay. So, this is the beauty of this particular method. Now, so I have actually got expressions for specific problem. Now, given that I am actually now going to solve a specific problem that I am going to give you, and that is that let us put it down. Let us put down another problem, and this is an example problem that I am going to solve. Let me take a situation where I have k. So, I am defining these as k k, okay, and I am not putting a dashpot in this particular case, it does not matter. Okay. This is a UDL, and I have a loading which I will say is of the following form. the loading is only here, where this is at this point the load is given as p bar of t. Okay. So, and this has m bar constant mass per length. Okay. And what I have to do is, and what is my degree of freedom? I will define my degree of freedom as the rotation here. Okay. We will define the degree of freedom rotation here. Now, I am going to solve this problem in two ways. What I am going to first do is I am going to solve this problem from first principle, and then I am going to use these expressions that I have. I am going to use these expressions in it. Okay. So, now let us go step by step, and that is first step what? Well, let us give it a displacement, and if this is unit, if this is theta, then at this point I have, I forgot to put down the values, and so I am going to put them as L by 2 and this is L by 2. So, the total length of the bar is L. Okay. So, then over here I have L by 2 theta, this is also L by 2 theta, and at any point. So, my x I am going to take as positive in this direction. So, this is x theta. This is my displacement. Okay. And if I look at it, so therefore, so now I need to find out the forces. I am going to write down the forces over here, and the forces are the following. I have, since this is undergoing displacement in this direction, okay, the force is going to oppose it. So, the force is going to be here, and this force is going to be equal to k L by 2 theta. Okay. Note that I have put both of them as identical springs k k. Okay. Now, here this spring is being subjected to this direction. So, it is going to oppose it in this. So, this force is going to be equal to k L by 2 theta. Okay. Then I have p bar of t. Okay. So, this is going upwards. Okay. And so, where this is p bar of t. So, this basically becomes then given by p bar, it is p bar at any point, the intensity is given by p bar x 2x upon L. Look at it, because if you put x equal to L by 2, this becomes p bar, that is p bar. If you put x equal to 0, which is 0, x starts from here, right, x starts from here. So, if you put x equal to 0, you get 0, and so that is the intensity. Intensity at any point p bar x of t is equal to this. Okay. So, that is the point. Okay. So, we have that. So, these are the forces, and on top of that, what do we have? Well, if I look at it, if I look at this particular direction, this is rotating in this direction, right. So, if I take in this direction, so this is going up. So, this is going to give rise to m bar dx into x theta dot. And if I look at in this direction, okay, since this is going down, this is going to give rise to m bar dx into x theta double dot in the opposite direction. Okay. So, understand from here to here the forces are inertial forces are upwards, and from here to here the inertial forces are downwards. Okay. So, this is a very important point to note, that because this is rotating about this point. So, I have got all the forces. So, now I need to just put down the displacement, virtual displacement, and the virtual displacement is del theta. Okay. So, I know that this is L by 2 delta theta, this is L by 2 delta theta, blah blah blah. Okay. So, now, so this is the work, all the work done by all the forces, right. So, note that these forces will do negative work, these forces will also do negative work. So, every term is negative, right. Okay. So, I am going to write that down, and if I write it down, what do I get? I will take the first one, this is k, all of them are negative. So, all of them are negative, k L over 2 theta into L by 2 delta theta, okay, minus k L by 2 theta into L by 2. These are the two, these are this one into this negative, this one into this negative. So, both of them are negative and in this form, okay. And then I have the mass. So, the mass, infinitesimal mass in this, from this 0 to L by 2, I have the work done as negative, and on this also the work done is negative. This is equal to x delta theta and this is x delta theta. This goes under, this goes opposite. So, all I need to do is, it's 2 times, so this is going to be equal to 2 times, okay, 0 to L by 2, and this is going to be, the force is m bar dx into x by theta. This is the force into x delta theta. This is the work done. So, integrated from 0 to L by 2 and twice, because both sides are doing identical work. Okay. And then finally, I have minus, and this is the work done, and this note is again negative work done. So, this is going to be 0 to L by 2. Now, note that P star x by t, that is at any point, this is going to be equal to dx, that is the load, and that into x by x delta theta is the work done. Okay. And so, this is equal to 0. Okay. Now, so if I put this in properly, what I get is the following. I get now m bar x squared 2, so into L upon 2. So, this is going to be, if you note that this is going to be x squared. So, this is going to be x cubed by 3, x cubed by 3 going from 0 to L by 2, x cubed becomes upon L cubed upon 3, and x cubed upon 3 in and x cubed is L upon 2. So, this becomes, what do you get, L cubed upon 24 2 times. So, this becomes equal to m bar L squared by 12, okay, into theta double dot, okay, and I am taking all the negatives, so I am making it positive. So, plus now k L by 2, so this becomes 2 into L squared. So, this becomes k L squared upon 2 theta is equal to, now the integral over here basically becomes, if you look at it, it becomes p bar x upon 12. So, this becomes p bar goes outside, p bar upon L goes outside, and this goes from 0 to L by 3, and this is x squared dx. Okay. And so, this becomes what? P bar L cubed by 3. So, this becomes L by 8. Okay. So, x cubed by 3. So, this becomes L by 24. So, this becomes P bar oh, I am so sorry, I made a mistake here. Please forgive me that this goes from 0 to L by 2. Right, exactly, it is 0 to L by 2. So, this becomes L by 24. So, what I have is essentially P bar L squared by there is a please note here, I have made a mistake. This one is 2. So, there is a 2 coming here, 2 p bar. Okay. So, what I have is 2 p bar. So, this becomes 24. So, this becomes p bar L squared by 12. Okay. So, what I have is my m star is equal to m bar L squared by 12, k star is k L squared by 2, k, and p star becomes equal to p bar L squared by 12. Okay. So, this is my solution. Now, if you want to look at what omega is equal to k star upon m star square root, and so this becomes equal to k L squared upon 2. So, this becomes square root of 6 k upon m bar L. That is your omega. Okay. And note that understand that p bar is a function of t. So, it is not as if we do not have a function of t. So, now let us see if I can use the equations that I have used. Okay. So, let us look at it, and I am only going to find out the k star, because everything else is again this thing. So, let us look at what this is. This is a situation where what is xi? Xi is the one where you give unit displacement corresponding to the degree of freedom, and you find out what are the corresponding values. So, the corresponding values over here are L by 2, L by 2, okay. And here this is going to be equal to x, and this is going to be equal to x. Okay. So, if we look at this, if you look at m star says what? It says 0 to L m bar xi squared dx. Now, note that 0 to L in this particular, because xi is actually a little bit different from here. So, why we get it is it is going to be equal to 0 to L over 2, because x goes from 0 to L by 2 in both directions. So, m bar, okay, xi is what? X squared dx, and twice of that, because I have m bar x 0 to L, m bar x 0 to L by 2. So, 2 of them. So, that becomes essentially, or I can pull it as 0 by L by 2 m bar x squared dx. So, note that x, always remember that x is what? It goes from 0 to whatever is my thing. So, if you look at this, this you get as m bar L cubed by 12. Look at k star. k star is k I xi I squared summation. So, k I is k into xi squared L squared by 4 plus k into L squared by 4 is equal to k L squared by 2, which is what you get. Okay. And p star is the same thing, you will get it, you will get p bar L squared by 6. So, therefore, xi by this is xi. If you use this, so you see whether you use this formulation or whether you use the other formulation or from first principles, you should get the same equations. Okay. So, I am going to stop here in terms of the generalized single degree of freedom. I have spent enough time on generalized single degree of freedom, and I shall give you some problems to do, which will help you in your own way get the equation, get involved, understand how to get m star, k star, c star, p star, all of those terms, so that once you get m star, k star, you see the point that goes back is the following, and that is the point that I was trying to make. So, now I have shown you that given a generalized single degree of freedom problem, first what do you have to do? First is define your degree of freedom. That is important, because if you do not define your degree of freedom, so therefore, your entire thing is based on thing. Next, get shape function corresponding to degree of freedom. In other words, get xi x. Okay. Plot it. Put degree of freedom equal to 1, okay, and then put your system, put it equal to 1 and find out what are the values that you get at different points along the length of the bar. So, that is the first thing. Third, well, get m star, c star, k star and p star. Now, you can get it from first principles, or you can get it from the formulation, the formula that I have given you. Okay. I would prefer you to solve it from first principles, purely because it just makes it that much easier for you to understand. Use the principle of virtual displacement and get it. Okay. So, get your m star. So, what is the fourth? Well, now you see this becomes where z is the generalized displacement. Okay. Z is the generalized displacement. Note that z can also be theta in a particular case. So, in which case m star, c star, k star and p star will be appropriate. Okay. So, the point then becomes that once I have this, what happens? Well, I have m star z double dot plus c star z dot plus k star z equal to p star. How is it any different from the single degree of freedom problem that I have solved? If I get this, I should be able to solve for z t or z max given p star of t will have some form of xi t, which would be harmonic or periodic or pulse or impulse or arbitrary finite duration load. It does not matter. We have already spent 14 lectures looking at how to solve this for a variety of different kinds. So, therefore, the solution, once you have got this, the whole problem is actually in getting the equation of motion, getting these. Once you get these, okay, solving this is identical to what we have already done earlier. Okay. So, that in a sense brings you down to the solution that, look, whether I have a single degree of freedom given by that one one story, one bay rigid beam frame, or whether I have a more general kind of problem which can still be defined by a single degree of freedom. Of course, note that in such a situation you have to have, it is an assemblage of rigid bars, because the bar can only move in a particular manner and you know exactly how it moves. So, that is one. So, it is an assemblage of rigid bars. Okay. So, we have actually solved the even getting equations of equilibrium for general problems. Okay. Next time I am going to show you that this generalized single degree of freedom problem can be extended for other kinds of problems. Thank you very much. Bye bye.